What's going on, everybody? This is Mr. Diamond, and today we're going to be going over our Section 2 of Chapter 6 of Physics. This is the conservation of momentum. And then attached to this, there'll be a separate video that has the example problems for it. So at the end of last chapter, we focused on how the law of conservation of energy could be combined with the ideas of kinetic and potential energy to solve for information. If you knew that there was the beginning of a system of something happening, a certain amount of potential energy and a certain amount of kinetic energy, you could predict speeds or heights or a bunch of different other things like that, just based on that initial idea and knowing whether or not there was conservative and non-conservative forces involved. So while energy and matter are the most common things we think of as being conserved, there's actually a few other examples in science. Things like electric charge. There's a couple of other ones, but the one we care about today is going to be linear momentum. So if there's not an external force acting on a system, then there can be no change in the total momentum of that system. This means, for example, like if you have two pool balls sitting on a table and one hits another one in a forceless environment, then the total momentum of each ball should add up to the original momentum. This is actually something you've already kind of done in a couple of the example problems, especially the one that involved the child being lowered into or pulled out of a wagon as it goes by. This is why our examples of changing mass work. That's what I was just talking about. We assume that the momentum is conserved, and we find a new speed based on that same initial total momentum. This relationship is creatively called the law of conservation of momentum. It says that the total momentum of an isolated system of objects will remain constant, and isolated in this case means the only significant forces take place between objects in the system. So what does significant mean? Well, the easiest way to think of it is to think of something really, really simple, like a simple exchange of energy, like a ping pong ball and a paddle. So when the ping pong ball is hit, technically there's a whole lot of forces going on. Friction of the paddle hitting the ball, the air resistance that is going to be occurring, both from the ball being hit and from the paddle moving, gravity pulling the ball down, all of these things are going to affect it. But really, the only force that's going to be kind of large is going to be the force of the hit, the paddle actually impacting the ball and causing it to go flying. All the other forces are not really doing a whole lot in that situation. So we would call that the only significant force. Yes, all those other things are happening, but they're really not going to be affecting it. The ping pong ball is so light and it's being hit so hard in comparison to all those other forces that we can kind of ignore all of the other ones, for most purposes at least. So the formula for conservation of momentum would look something like this. P1 equals P2, very straightforward. Or if you break it down for any number of components, so this would be like if you change the mass of an object 1 into a different, like it started as 100 grams and ended as 200 grams, the momentum at the 2 points have to be identical. Or if you have a system of things, you could have the momentum of thing A at position 1 plus the momentum of thing B at position 1 plus however many things there are involved should equal the momentum of thing A at position 2, B at position 2, and however many numbers of things there are at position 2. Usually there's only going to be one or two things involved, either one thing changing mass, or there'll be two things that are colliding with each other. So we've got a couple of examples. A 10,000 kilogram train car travels at a speed of 24 meters per second before it hits an identical car. They then lock together. So if you've ever seen the back of trains where they have the cars, when they hit, this one's actually going to lock into place and they're going to continue traveling together. But assuming momentum is conserved, we want to know what speed they have. And then we're going to calculate how much recoil a 5 kilogram rifle that fires a .020 kilogram bullet at a speed of 620 meters per second would have. We're going to also be assuming in that one that the rifle is fired at rest. And then finally, we've got a pretty tough example, a pretty lengthy one here. You and a friend are riding in a spaceship trying to escape from a rapidly approaching solar flare. Your ship weighs 23,000 kilograms and is flying at 35.0 meters per second. You and your friend each decide to lose weight to increase your speed. Your friend ejects 1,200 kilograms of supplies out the back at 5 meters a second, while you are indecisive. You can eject 3,000 kilograms at 3.5 meters a second out the back, 6,000 kilograms at 5.2 meters per second out the back, or you can detach a 10,000 kilogram thruster on the underside of the ship. If you can only do one, which one will most increase your speed? So this is a very lengthy, going to be a good critical thinking problem. I'm going to work those out in the separate video underneath it, but I believe that's all I've got for conservation of momentum, and then we're going to get into collisions. So this first section is kind of more concerned with just having one object changing or breaking apart into two things. This next section here is going to be actually one object hitting another and then moving on. We'll talk about that when we get there. So that's all for just this very brief set of notes. In the meantime, if you've got any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.